My name is Jiri Olsa. I work for Red Hat. I'm making the perf system for Red Hat Enterprise Linux. And I also contribute to upstream. This presentation is basically about the feature that I was involved with and never made it to upstream, so basically just not to forget about them and maybe increase the awareness. Yes, something what will come in the future, but still didn't meet the the expectation for the upstream for the features to be actually managed. I will start with the threads support in the perf tool because that just got a lot of attention. Basically, thread support makes some sense for record and report tool, and once we have this support in those two commands, basically we can inherit them. The other tools will just make use of them, positive use of them. It all actually started with the record command. Him send it RFC packset which actually implemented the threads in the perf record, and it actually showed that it could make, in some cases, speed up of 30% speed up in the record time. So for really big files, it makes a difference. The idea of the feature was that basically, if you want to process data in separate threads, you need separate data. But in perf, we have the data in one data stream. So the first thing that was needed to implement was to split the data during the record. So there was this perf record index option implemented, and that actually split the data into multiple data streams. And at the end, all of those streams were matched in the data file, so it still was, at the end of the day, it was still one data file. And then perf record that new option --multiple thread, and for each data stream in the data file, spawn the thread and make like this. Well, every thread was processing its own data stream, so that's where the increase came from. As easy as it might sound, there were actually many rough edges and some design issues, so it actually never made it to the main line, to upstream. It ended up only as a RFC, which you can see there, and yeah, from the time nobody actually else looked on it. But the speed up is very promising. We continue to revisit this feature in the future. That was record. A record is sort of another story. Basically, currently single threaded record, the duty of that process is that it creates events. Whatever user specify, we create events for every CPU or whatever user specify. In the command line, we create the events, and we create the memory map for every CPU. We create separate memory map, and the single thread in perf record actually goes through every memory map that we have, checks if the memory map has some data, if there is some data stored to the data file. The memory map is classic circular buffer with two pointers, head and tail. Basically, the perf record is the consumer of the data, so it checks the head pointer. If there's some data, the tail pointer is different. Whatever is in between is stored to the data file, and we move on to another memory map. The kernel itself is storing the events to it's the producer of the data to the ring buffer. So basically it checks the tail pointer, checks if there's enough space for the new event. If there is, it stores the event, perf record, you'll see it, eventually it's stored to the data file. So that's the idea how we check the memory maps and store it in the data file. Eventually you can get to the point where the memory map is actually full, and that means that kernel will start losing the data. So whenever there's an event generated and the ring buffer is full, kernel just trash the event and moves on. And this can actually happen. When there's a lot of memory maps and the single thread just cannot keep up with this sort of data. So if you have like a really big server with hundreds of CPUs and you ended up monitoring a few events, you need to create memory map for every CPU in the system. And if you request for the sample to store some really not big but some data, like core chains, the single thread will actually not keep up with the production of the events and inverse, and you will start losing the data. So that's where the threads coming to the pictures. The idea of the initial implementation was that basically we start multiple threads, and they will take each of the threads will take some portion of memory maps in some intelligent way. They will be like separated between threads. This way, the threads will keep up, and we will stop using big events. So that's the threads approach. Connected to this feature, not really threads related, is asynchronous I/O writes to the perf data. It actually appeared like a few weeks ago, and it's original work from Alexei Budankov. He posted the patches and implemented it, and it will be merged in soon. Basically, the idea is to switch the standard writes that we are using at the moment to the data file for asynchronous I/O writes, the write through the POSIX IO API, and you can actually see some really nice announcement in speed. So basically, this is not involving the threads, but it's actually solving the sort of the issue that we are trying to solve with the threads in a different way. So we will have soon the perf record dash AIO option that's doing the this asynchronous write, and in the future we will have also this perf record dash threads, which will create those separate threads and use that. So much for the threads. Another feature which never made it to the upstream is delayed retrieval of user space data when you generate the sample. The idea is from Peter Zylstra. Basically what happens when you monitor hardware events is that for each sample there is an NMI generated, and within this NMI the kernel needs to allocate the data in the memory map and store all the data that user requested for the event. If user requested to store the user space data, the kernel needs to go to the user space memory, which is quite costly, and within the NMI, retrieve the data and store it in the sample. That's something, if something like this could be avoided, it's a good idea, because NMI is very expensive context when CPU is in the NMI, basically nothing else can run. Not any other interrupt can be run on the CPU. So Peter came with the idea to move the user space data retrieval from the NMI to later processing. So basically create two events. In the NMI, we would create just the basic stuff without touching the user space data, adding some sample ID for later processing. And whenever, at the point when the NMI finished, we would create another event, not in the NMI context. So, and we would create another event with just the user space data, and the perf tool afterwards would connect those two events together. So that would basically lower the time. The idea is to lower the time spent in the NMI, and that's what we try to implement. Peter Zilska actually also recommended what to use for the second part, for the user data event. And we are using the task core, which is like mechanism in the kernel. When you are in the syscall, you can schedule work that will be executed before the process is going back to the user space. So whenever we are in the NMI, we check if we are in the trigger window where we can actually schedule this task work. If we are, we will in the NMI store just this simple event, which is some sample ID, and schedule the task work. NMI will finish, syscall will finish at some point, task work will get scheduled, and we will store, before we return to the user space, we will store the user space data. We actually made some implementation, and we achieved that we were able to actually see some improvement. But as you can see, it really wasn't that big enough. And also, basically, we were splitting one event into two events. So the perf tool processing afterwards was also really costly. So for those two reasons, this feature never made it to the upstream. And I guess we are waiting for some another speaker's idea how to make it right. Yeah, there's an original RC code, and I also have the code in my Git branch if somebody's interested. Another feature, this is a very light feature, but proved to be useful still within both the out, is the watch command. Some time ago we were debugging some scheduler issue, and it came to the point where we needed to watch the scheduler data that goes out in the proc files, like the sketch/debug files, and it's quite massive file with a lot of information which you cannot just easily grab for the fields that you are interested in. So we created this field that basically allows to parse several debug proc files and display the fields, and it allows you to specify which fields you are interested in, allows you to store the data to the data file, and zero the counters, because some of the counters are going from the boot time, so it's very hard to see the increment. So it has also the way to zero the counter, so you can get a better idea how the counter is incremented. I can actually show you this one. So, if you run perf watch, you will see the support for the debug files that we offer. As I said, we use it initially for debugging the scheduler issues, so it's mostly scheduler right now. The idea is that you write perf watch, for example, RQ, and it will parse out the running queue data from the skate debug file and display you in a way so you can basically see how the counters get incremented. The red ones are actually which are changing every interval, every second. The white ones, these are counters which wouldn't change for more than 5 seconds, and the green is just in the middle, like between touched and not being incremented at all. So you can, I was using it also to debug some perf data. It allows you to parse also the interrupts file, so you can get the idea of how the interrupts are run on your system. And there's this EMI interrupt, which basically shows you the perf NMI stats, how many times the perf NMI was triggered on the CPUs. So if I run if I run something that will actually proc CPU free, you will see that the NMI watchdog gets triggered because the CPU is now busy, and the NMI watchdog is basically implemented by perf. So you will see the numbers increasing. If I run if I start to actually monitor the CPU free, you can see that perf is now monitoring the CPU free and is issuing the perf NMI interrupts. So you can see the CPU free is actually incrementing much more. And if you use that 0 option we have, you will actually get some straight values, and 4000 is like this default frequency that we use in perf. I didn't specify frequency, so it's 4000 per second of the EMIs issued in 5 seconds. You can also plot the data. So if you write CPU free, EMI field, and the data. It's still in the progress. Basically, it allows you to write the data to the data file and display it like in a blue plot. You can get it out of this branch. It's semi-working, as you could have seen, and the status is that basically they need to make it work properly and probably make it more generic and see if it's any useful in the future. Next feature is the CPUTIME EMU. Some time ago we were asked on the mailing list that basically perf is not really able to show you the idle time. Like you can measure whatever your workload spends the time in, but you never see it in the perspective, like how much of the system was idle. And that basically why I created the CPUTIME EMU. It's basically mirroring the counters that are provided by CPUTIME subsystems. This subsystem basically keeps all these counters, like users of IRQ, IOA, IRQ, all those counters per CPU. So, and this DMU provides all those counters through the perf interface, like perf events. It also we made binding for the perf stat, so now you can write just perf stat top, and it will display you those counters in a nice way, which actually I'm going to show. I wrote per stat -top with the interval of 1 second, and you can see the basic set of the counters, and those counters are calculated for the whole system. It's like I would be using the shade. The shade is by default. So those are the counters gathered from all the CPU and aggregated all together. You can, of course, use all the other per stat options to display the different aggregation. If I do. Yes, so you can use all those aggregation options that we currently support, and basically view the state of the system. You can see I didn't switch off the hot from the CPU free, so if I actually kill that, we'll get back to normal and do all that. This idle system. Then you can use, for example, per core, and then you will see the result group by core. There's one slight issue with this feature, and that's probably the reason it hasn't been merged yet. If you have dynamic ticks function enabled, which you probably will have, it can happen that the counters will be incremented every second, and the first stat will get just wrong data. We need to somehow work around it, but once we get that, we will put this feature upstream because it seems useful. There's the RC post and there's the retrieval. You can actually find the code. BPF command is another feature. At the time that we were actually adding all the BPF code to the perf, we are thinking of doing something more, because currently what perf allows is to take a BPF program, attach it to the event, and store whatever the BPF program is doing, store like event in the data file. In discussion with Arnaud, we actually wanted something like btrace style like approach, basically something that's doing the BPF trace or the BCC, but it would be written in the C, so we would have just one single C file, and part of it would represent the eBPF program, and the rest would basically execute those pre-post handlers, and they would be basically the callbacks that are common for BCC or BPF trace. But it all would be in the C. We have actually some prototype. It works nicely, but it's in C, and the difference between processing the data in Python and in C is really considerable. So we let this feature alone for now. There are better tools to actually do this RDT support. RDT stands for Intel Resource Directory Technology. It's basically a new feature on some of the Intel CPUs. You can configure the shared resources like cache and memory in general. You can classify them, and for each class you can assign different process, different CPUs, so you can somehow rule how the cache will be used by your application. And this has, of course, big impact on the performance. So we wanted to store this configuration of the RDT feature in the perf data file. So when you actually look on your profile afterwards, you can see what was the RDT configuration. The RDT configuration is done by RES control file system. It's a new file system which was implemented. Basically, you mount it, and in the directory you will have several control files, and you can create like directory to create new class of the cache resource and assign new schema for the class. So basically you end up with some directory tree. We basically check for the directory tree and dump it to the data file, and then in the record phase we allow to display it, and even actually take the configuration and apply it to the system. So if you are on the same machine, you can basically recreate the environment where was your profile made. This is not in the main line for basically two reasons. The feature in kernel there was huge rewrite of the feature, so it needs rebase to the new design. And also, I saw like these features being disabled on some Skylake processor, so it's probably suffering also on the hardware level. It isn't so much used as far as you can see, so that's why it wasn't being posted. Even triggers, just briefly, it's a feature that we touched quite a few years ago together with Frederick Weisbecker. Basically, it allows you to create an event that will trigger another event. So you could say that you want to monitor cycles, and then you would say, I want to monitor cycles only when it goes to IRQ entry that would actually enable the cycles, and then disable the event when it goes to IRQ exit. So at the end of the day, you would get the profile only within the IRQ paths. So this feature never made it. We made like really. There were some design issues, and also the interface. We couldn't come up with something easier than this, and nobody actually liked it. So yeah, this never made it. Group sharing. This was the effort to basically when you monitor, for example, trace points and use the wildcard, you ended up using many events. And if you are not root, you might have number of descriptor limited to your usage. And so basically we came up with a feature that only the group leader, if you created events in the group, only the group leader would return the file descriptor, and the rest in the group would be governed just by the group leader. So that would actually allow to monitor quite many events, even if you are in the restricted environment and you cannot create many file descriptors. Yeah, this is one very long to-do list, so let's see how it goes in the future. And the last one, some time ago we we re-implemented the build system in the perf, basically to match the kernel build system. So basically we allow the config options And it's just a very short step to provide something like many configs. When you configure the kernel, you can actually get all the configuration data to this .config file. And we are thinking of having something like this for the perf. So you could basically end up compiling the perf with the commands that you would choose. For example, you would have perf just with the record or record command, or compile out tests. So yeah, it would allow to cut the dependencies, and it's also good for the code quality and the separation. But yeah, we were thinking maybe the embedded guys would like to see that, but nobody actually came to us and pushed for that. So I guess it's not that bad. That's it. I have. It's all the screw-ups here.
Any questions?
A lot of new stuff is added for perf and for the X kernel. Are you, as Red Hat, actively backporting the perf enhancements to your cheat of the 10 kernel in Red Hat 7?
Yes, usually in RHEL we backport whatever we are asked for. I'm trying to keep at least the perf tool close to the upstream as much as possible. It's not so easy with the kernel code, but we are basically backporting all the major features.
Other questions? Thank you.